Hello, my name is Binder. I am presenting here a time-discrete SO3 three-jump sequence showing a quantum-type orbital wave dynamics. Many thanks to the organizers of DANOC. Let's start with a small introduction. The time-discrete SO3 cross products are part of a time-discrete nonlinear signal jump sequence and mainly based on recurrent SO3 cross products. And here is the formula. There are different time labels. So this is the new vector. This is 2 times 2 steps ago vector, the last vector, crossing a sum of coefficient times functions depending on previous values. So there's very likely some chaos nonlinearity in those vector functions here. They are all part of three-dimensional space. If we multiply our autonomous dynamical equation by t-1 location, you get a 0 part involving the functions because of the cross product is orthogonal to the t-1 location vector. So you get an invariant scale, which is a symmetry, and where we have a cosine of the rotation angle related to the vector angle between the 2 subsequent locations. 2 subsequent locations with difference of one time step are very important for the concept of polarity. We will find something like a charge, and we discover it as a very basic ingredient in our dynamical equation because we have a built-in reflection. Originally, I was inspired by Christos Skiadas showing some von Karman type patterns that emerge out of nowhere in a very simple 2D recurrent equation. And one part is a translation, say one step in this direction, and one part is a rotation up, rotating down, rotation, and this up and down is a reflection, or of course a rotation. And the reflection operation is very important for the dynamics and responsible for spatial separated alternating even odd number tuples with opposite signs. So the polarization is due to reflection mainly. Combining reflection with rotation and translation generates very small geometric shifts after every loop. And these are the pattern generators, more or less. And many loops provide for pattern formation and dynamics. The field functions we have shown in slide 1 can be understood as a part of involving a kind of vector gradients in the difference and in the shifts, even potentials, and we can work with a vector Laplacian and vector double densities. So if we apply some boundaries like Gauss' law and symmetries, we find some equations, additional equations, that involve, say, a Laplacian or whatever. because we operate on a cross product, and we can also have terms with double cross product after two loops. So it's straightforward to generate an algebra and also symmetries, which is of course a challenge. And so we could also find a context probably that could be linked to quantum electrodynamical physics. In a visual approach, we have such things like this pattern is generated. You see it at the start. Here it is with different colors. It has a small core and something orbiting very quickly around it. So it's very straightforward to make a new concept about, say, charge surrounding each other or attracting each other, maybe some kind of vector equations of Maxwell type or whatever. This is quite open, so it's just the beginning. The core set at the orbital center emerges very often. Here we have two rings at the center and two orbital clouds, like a dipole cloud, left and right of the center. And we see here the outside charge in blue with even numbers and the inside locations in red. And the jumps are always in, out, in, out, in, out, in, out, in, out, left, center, right, center, left, center, right, center. So they're jumping according to the setup and the initial conditions and to the boundary conditions and the parameters and the field functions. So there could be more center charges and or more orbital charges or whatever. What we also have here is a very simple case of minimalistic field functions. We have 1, 2, 1, 3 label, say, regarding our initial formula. Here you see if I j is here 1, 2 and 1, 3. 0 is just RT, 1 is RT minus 1. And so we have here -1 and -2, or -1 and -3 combined with coefficients. These functions are very simply 1, 2 is R minus 2 divided by the sum of t minus 1 and t minus 2, and 1, 3 is R t minus 3 divided by the difference of t minus 1 and t minus 3. So they are very similar, shifted by 1, but opposite sign, which is also, of course, due to the reflection. We find a sharp transition between such a structure, to a ringy structure with fixed points, and often on a sphere, and a transition to a more hyperbolic formation, where the coefficients here are more or less in a ratio about the square root of 3. And I will show it in a few minutes. These are my references. I had already, this is the inspiration by Skiadas in 2009 at the Chaotic Simulation Conference. And the last 2 years I was presenting in at this conference more or less the basic of this cross function, cross product concept, and three-dimensional rotating axis extension. Skiata started in 2D without rotating a rotation axis. It was a fixed axis, and now we have a moving or rotating axis due to the cross product. So let's jump to the simulations. I've written a program. I'll quickly jump inside, where you see those dynamic movements. These patterns are highly dynamic. It's a normal info processor. You see a lot of dynamics. It's a very minimalistic generation of patterns and fields. And you see some interesting objects, and well, they can be very crazy, geometric, funny. Never seen something like that. It's very interesting. But yes, of course, there are structures that from a point of physics interesting, and I'll find one. There are a lot of things, of course, such waves, not with center, but they are orbital wave functions, geometries. And here, funny thing, 6 units. Every unit, we have 3 positive, or 3 negative, or 3 odds and 3 even. And they have their own excitation inside, you see. And here is a pattern with a lot of fixed points, drift. Again. And here is how more or less more like atomic formation and patterns. The core at the center, we can zoom in. So in the center there is also a structure related to the structure on the outside. And here you see a lot of dynamics. We have a modulation, a long wave modulation of a shorter orbital wave. And also in the core. The core reflects this motion in the orbit. And yes, it's a three-dimensional cloud, and it's a wavy motion. So there are a lot of waves, maybe wave mechanics at work. These are very new findings. You can see them on the web page, on Yahoo, on YouTube, sorry, and I will show you a link. It's a hashtag DACOP. So here you see the core, very small, 1,000 times or 2,000 or 4,000 times smaller, and yeah, it's the counterpart, and the signal dynamics is jumping in, jumping out, jumping in, jumping out, with a small shift generating those wavy and waves and traces and orbits. And here you have also separated units on the orbit, course, there should be also separated units in the center. Let's see. Very small. Yes, also in the center. There are two very, very small separated units. So there are a lot of funny clouds with their own characteristic numbers. And finally, we get to this point here. It's a very chaotic core. This here is a core. Let's zoom out. Zooming out of the core. We get a chaotic satellite that has like a jittering motion. And it's funny. And the core is also very chaotic and jittery. So there could be also chaotic processes involved, which is very interesting. So shoot in, shoot out, jump in, jump out, different ways, geometric, different kinds of shapes, and straight rays from the center to the outside and back. Very interesting. And switching between those and spherical, say hyperbolic to spherical, is very interesting. So thank you. This was my presentation.